All right, we are now ready for factorial design. It's another way of saying a two-way ANOVA. So with a two-way ANOVA, you have two independent variables. So I have some examples here for you, and I hope you can see how this could be useful. So imagine you want to understand the effect of a drug on somebody's anxiety level. Well, it could be that the age of the patient, we see here, independent variable number 2, would modify the effect of the drug. So we might need to manipulate both of these to see how they impact anxiety and how they interact. Similarly, if we want to look at anxiety level as a function of type of therapy and length of therapy, it could be that we can't just look at type of therapy, that some of the effectiveness might occur after a briefer period than in other ones. So we might want to look at both of those. Same thing with weight change. You might not want to just look at exercise or diet, but both of those. And the simple example I'll work through is with satisfaction with the toy. You might want to include both toy color and gender. So to recap, this is similar to a one-way ANOVA in that you have an independent variable that can have 3 or more levels, and you're looking at an impact on a dependent variable. The difference with a factorial or two-way design is when you have these second independent variables. So the key advantage is you compare the relative influence of the independent variables on the dependent variables, and you can also examine the interaction. And I'll explain more about that here in a second. Okay, so let's work through a simple example, and we'll talk through some terms of a study where I have an independent variable and I have toy color. I'm going to vary that between blue and pink, and then my second independent variable would be the gender of the toy recipient. So I'm either going to give this toy to a boy or a girl. And then the dependent variable would be the satisfaction with that toy. So there's some terms and language that you need to understand when you're working with two-way ANOVA. First of all, factors has to do with, factors are the sources of variation in the dependent variable that the experimenter controls. So I'll say that again. It's the sources of variation in the dependent variable that affect the dependent variable that the experimenter controls. So there's 3 basic factors in a two-way design. There's the A factor, which in this case, capital A would stand for toy color. There's the B factor, which in this case would be gender. And then there's the A by B, which is written A times B. That will be the interaction between those two and how it affects gender. Excuse me, how that affects the dependent variable satisfaction. So the levels are the values that the independent variables take on. So little a corresponds to big A, which I said is toy color. And the levels that toy color takes on is blue and pink. So little a numerically would equal 2, representing blue and pink. If there were 3 toy colors, blue, pink, chartreuse, then little a would be 3. Little b is equal to 2, because in this case we have boy and girl. If instead I had boy, girl, and undisclosed, that would be then 3 levels, and b would equal 3. The design specifies how many levels I have of another independent variable. So the design in this case would be a 2 by 2. If I had 3 colors, then it would be a 3 by 2. If I had just, if I had boy, girl, and undisclosed, then I'd have a 2 by 3. All right, and then we talk about, there's 2 kinds of effects we can get. We can get a main effect, and that's when an independent variable directly affects the dependent variable. So there's 2 possible main effects, one for toy color and one for gender. And then there's also the interaction that's possible. And an interaction effect means that the effect of one independent variable on the dependent variable depends upon the level of the other independent variable. So I'll say that again. An interaction is when the level of one independent variable, its effect on the dependent variable, depends upon the level of the other independent variable. Okay, so let's look at some of these terms and concepts in a specific example here with some data. So you see here I have toy color, which I'm going to consider to be our A factor, and sex or gender is going to be our B factor. So to start with, if I want to determine if there's a main effect for toy color, I want to compare the overall blue scores to the overall pink scores, ignoring whether somebody's a boy or a girl. So what we do in that case, to look at the independent effect for toy color, we collapse across boy and girl. So imagine here just erasing this line and this line so that I have one column here and one column here. And for the moment, I don't care about gender. I'm just comparing the sample mean to the sample mean. So that's looking for a main effect for toy color. I collapse across sex. In the same way, I can compare overall boys and girls and see if there's a main effect for sex. In this case, I'd be collapsing across toy color. So imagine erasing this middle line here and this middle line here and just looking across to the sample means. So to look for a main effect, what I need to do is either compare the column means or the row means, and that's how I determine if there's a main effect. So the third thing we need to look at, remember there's three factors, the A factor, the B factor, and then the interaction between the two. So the interactions here, I'm going to look at the cell means and plot those on a graph to determine if there's an interaction. Unless you're some kind of genius, most people have a hard time seeing the interaction just looking at the cell means. They need to graph it. So one way to graph it would be like this, is to put one independent variable on the x-axis, and that's color. So you can see blue toy and pink toy. And then you can see the boy and the girl, the gender is represented by different lines. So let's look at girl to start with. If I go back, you see I have, a girl sample mean of 5 for blue toys and 11 for pink toys. So I plot that. So a 5 for blue toys and an 11 for pink toys. Then I connect those dots, that's girl. Then for boy, I have a mean of 6 for blue and 3 for pink. So I plot that. 6 for blue and 3 for pink, and I connect that, and that's my line for boy. So how do you tell if you have an interaction? Well, if the lines are non-parallel, that suggests that there might be an interaction. Now, you still have to conduct a test for significance to see if it reaches significance, but just having the lines being non-parallel means that there might be an interaction. Notice the lines wouldn't have to be crossed necessarily, they just have to be non-parallel. Okay, and then what would we specify as our null hypothesis? So you would specify a null hypothesis for each factor, and remember with the two-way ANOVA, we have count them, three factors. So for the independent variable, my null would be the mu of blue is equal to the mu of pink. For gender, it'd be the mu of boys is equal to the mu of girls. And then an interaction, I would simply say no interaction. So just like before, we're setting our null hypothesis equal to 0 on effect, saying there's going to be no differences between our groups. Okay, so here we have the data that you would put in for SPSS. It's a little tricky going from the just a chart where I give you some numbers to how you would actually put it in. So I have a video that explains that in gory detail that you can look at later. Let me just give you a quick overview right now. So what we have here is color, which is one of your independent variables, sex, your other independent variable, and then satisfaction, your dependent variable. So it's like a one-way ANOVA, except there's this second variable stuck in the middle between your first independent variable and your dependent variable. So we have to divide color into blue and pink, so that's what the 1s and 2s stand for. And then for sex, we need to show that how there are boys and girls for each color. So here's blue, boys and girls for blue, and then here's pink, boys and girls for pink. And then your satisfaction scores. So once you get those typed in, then you're ready to go ahead and go to variable view. Let me say quick that there's two kinds of n's we'll think about. The little n is how many there are in a cell, and the little n here you can see is going to be 3. These 3 people are in the exact same condition. These 3 are in the exact same condition, etc. And then how many n do you have total? Large N will be equal to 12 because we have 12 people total. And when you get there, you'll move the dependent variable to the box that says dependent variable, go figure. And then you have your 2 independent variables, and you move those to the fixed factor box. And then we're just going to ignore the random factors. Okay, so that's setting it up, and then we got to hit these other 3 things, the plots, Posttalk, and the options. So for plots, we want to get a graph, and the way we do that is we move over the 2 variables. So typically what I want you to do is move them over in order, so color goes first and sex goes first. Unless one independent variable has more levels, then it helps if you put that on the horizontal axis. So let's say that we had color and sex for some reason had 3 independent variables. So boys, girls, and then cross-gender. That would go then in our horizontal axis. When you're doing this, you got to put this one in, hit add, and that sets up the plot, and then you're ready to hit continue. All right, then there's the Posttalk. We need to do a Posttalk only if we have a variable that has 3 or more levels. In this case, I tried to start with the simplest case. You just have color, blue and pink, sex, male and female. So you don't have any Posttalks because nothing has 3 or more levels. Remember, the Posttalk takes the variable and it shows you which means differ significantly. Okay, then step 4, we got to click on options as well. And what we're going to do here is just leave these all here and click on descriptive statistic, and that's it. That'll give you the means and the standard deviation. Okay, so here's what the output looks like. This first box just gives you the number of observations in each cell. So you had 6 in each cell. There's a total of 24. You can look here and make sure that you set it up right, you put the data in right. This descriptive statistics box you'll use when you're trying to write up the ANOVA. So I need to show you where you get the both the means to plot the interaction and where you get the means to test and see if there was a main effect. So first off, let's assume I'm interested in whether there was a main effect for color, for blue versus pink. If I wanted to look at that, I need to collapse across boys and girls. So I'll give you a hint. It has the word total next to it. See which 2 means would I compare if I wanted to see if there is a main effect for color. So stop it for a second and see if you can figure that out. Okay, so what should you have said? If you wanted to see if there was a main effect for color, blue versus pink, you would compare the total for blue to the total for pink, the 5.5 versus 7, and that will be the means that you use to test to see if there's a main effect for color. Then the second independent variable that you would look at is sex, and you'd want to see if there's a main effect for sex. So what would you look at there? Well, you would then compare boys overall to girls overall, that 4.5 and that 8, ignoring collapsing across gender. So you're either going to use these 2 totals or the total box down here and the 2 levels of that. And then last of all, you're going to want to be able to identify what cell means are used to show the interaction. And so the interaction would be plotted using this mean here, the 6, the 5, and then the 3, and the 11. Now you won't do this, the computer will do it, but I want you to know where those means come from when you're looking at the graph of the interaction. Okay, moving on. Now you get to the source of variation table, and this has all the sources of variation that are going to affect our dependent variable, which is satisfaction. So it looks similar to the one-way ANOVA, but it's a little different. So first off, let me show you some things that you can ignore, which you will appreciate. So what can you ignore? You can ignore this first line where it says corrected, this line where it says intercept, and this line down here where it says total. When we do this, we're always going to be using the corrected total. So what do I have left? If you look at this, I have these three things here, the color, sex, and color by sex, and then error and total. And it should look familiar in that you have some sum of squares, you have some degrees of freedom, you have mean squares, and you have f. And then you have a significance test for each f. So let's go one step at a time. You've got, in essence now, what you can think about as 3 between group factors: color, sex, and color by sex. If I follow color across, I'll see that the f for color is 6.75. Is that statistically significant? Yes. So I'd say there's a main effect for color. Second question, is there a main effect for sex? I'd look at that, I'd carry that across, I'd see there's an f there, 36.7. Is it statistically significant? Yes. And then I come down here to color by sex. Is there an f that's statistically significant? Yes. Excuse me. So I have 3 significant effects. In other words, each of my factors, the A effect, the B effect, and the A by B, they're all statistically significant. So you can look at the following slide while I stay on this slide to see where the formulas come from. So where do the mean squares come for this f value? I'm going to take the mean squares for color, that's 6.750, and divide by the error term, which in the fluke of convenience works out to be 1. So 6.75 divided by 1 is 6.75. Same thing for sex. How do I get the f value? I take the mean squares for sex divided by the mean squares error, and that gives me the 36.750. Then the same for the last one. I'll take the mean squares for the interaction, color by sex, divide by error, and that gives me the f. So in each case, I'm taking the mean squares on a given line and dividing by the same error term. And error is just another way of expressing within group variance. So I'm always using the same number on the bottom, different numbers on top to get these f values. And then you might say, well, where did these mean squares come from? Well, just like on the one-way ANOVA, we take the sum of squares divided by the degrees of freedom and we get the mean squares. So if we look here for color, I have the 6.750 divided by 1 that gives me the 6.750. Or if instead I was looking at or if I was looking at sex, how did I get the mean squares there? I take the 36.750 divided by 1, and I get the 36.750. So 2 more things you should note. If I want to double check my values here, if I take color, the sum of squares column, if I take color, sex, and color by sex, and error, that shall add to my corrected total of 112. Same thing with the degrees of freedom. I take the 1 here, the 1 there, the 1 there, add 8 to it, I should get 11. Remember, we're always going to ignore that total line and use the corrected total. Okay. So, just to recap that there, the 3 F's that you get, those are 3 effects, it could be affecting the dependent variable. You get the s by taking the mean squares between groups, or the mean squares for that factor, divided by mean squares error. How do you get the mean squares? You take sum of squares divided by degrees of freedom. And then where did the degrees of freedom come from? Well, there's these different formulas. Note that little n is the number of participants per group, and large N is the total number of participants. So you can work through the math here and see how that works out. So if there's 2 levels of A, and remember A is color, 2 levels of A, it's 2 minus 1 or 1. 2 levels of B, B being sex, 2 minus 1 is 1. And then what about the degrees of freedom for the interaction? It's A minus 1 times B minus 1. Well, that's 2 minus 1 is 1 times 2 minus 1. So it's 1 times 1, or 1. Okay, so here what it would be for degrees of freedom error, it'd be A times B, so it's 2 times 2. Remember, that's because we have, for color, we have blue and pink. Sex, we have boy and girl. That's 2 times 2, and then n minus 1. I set this up so it'd be very simple, so we just had 3 per group. So it would be 2 times 2 times 2, which would be 4 times 2, also known as 8. And that's how we get the 8 degrees of freedom there. Okay, so how is this going to work? In this class, I will always give you the sum of squares. You're not going to have to get those on your own. But once I give you those, you should be able to get the rest of it all the way through F. And then the F test here, if you're not doing it on the computer, you can look up F critical with the degrees of freedom, 1 and 8, 1 and 8, 1 and 8. Okay, and then you have your graph, which is very similar to the one I showed you before, right? So the line for girls and the line for boys, since the lines aren't parallel, it suggests there might be an interaction. Is interaction significant? Yes, because color by sex is a significant interaction.